All right, hello class, and welcome to the second part of this course, where we start talking about spacecraft navigation. So specifically, we're on, looks like lecture 8 here. So in this lecture 8, lecture 9, and lecture 10, and then when we come back to it, lecture 14, and to some extent actually the course on rocketry, we'll be talking about navigation. Now, navigation in space, surprisingly enough, is not quite as simple as navigation down here on Earth. For example, if I were to ask Siri here how to get to campus, hey Siri, navigate to ASU.
Getting directions to
She tells
Arizona
me,
State University
and
Tempe campus.
brings up a map and tells me to get in my car and take a left and take a right and so on and so forth. However, if I'm sort of intrepid and say, hey Siri.
Starting route to Arizona State University Tempe campus.
Hey Siri.
Head north.
Navigate to the moon.
One possibility is Four Seasons Resort Scottsdale on East Crescent Moon Drive.
Yeah, that's not where I want to go. And that's not just a joke. Navigation in space is quite complicated. Whereas on Earth, right, we have, here I am, there's where I want to go. Well, they always say the most direct or fastest way to get from point A to point B is a straight line. In space, that's not necessarily true. In fact, actually, if you went this way in a city street, right, there might be a building in your way and you actually have to go around. So particularly, you have to take the streets. Now, there are no streets in space, fortunately, although maybe there should be. There are airspace regulations which constrict you to flight paths in the air, even though there's no streets in the air. But it's even more complicated in space. So let me see if I can illustrate that a little bit. So say, for example, here I am, and Siri was cleverer than she is. And I asked her how to get to the moon, right? So say I'm like right here in a parking orbit, for example, going around the Earth in a circular parking orbit. The moon's going like that. And well, what's the fastest way to get to the moon, right? Well, I can say I will take a straight line. Well, what happens if I take a straight line? So I burn my Delta V rockets really fast so that I'm heading towards the moon. Maybe I do a big Delta V right there. What happens is, well, if I burn a little bit, right, say Delta V like 3 kilometers per second, what will happen is that the velocity that I have will be partially canceled out by that velocity, and my final vector will be like that, and I will go like, boom, there, back to the Earth. So not a great way to get there. Likewise, let's take another example, right? Say I'm orbiting the Earth, and here, this is me, right there, and here's a space station or something I want to rendezvous with. It's right behind me, not very far. Say it's like just a couple kilometers. I say, hey, there's my space station. I'm gonna do a little Delta V burn, go that way. Well, what happens is that I cancel out a little bit of the velocity I have, and my trajectory ends up not, well, going directly to the space station, but going again into the Earth, because I've now don't have I've lowered my periaps, so I'm just going to crash into the Earth, and the space station will fly right over me. So again, right, navigation in space is significantly more complicated than navigation here on Earth. These couple examples I gave here are actually can be better understood using the CW equations, the Colosi-Wilshire equations. I think there's actually a hill in there, depending on who you ask, who named those equations, which is linear orbit theory. And we're not going to actually cover that at any time soon in this course. But just to illustrate the difficulties of navigation around in space. Oh, here's another good example. If you're in an orbit And you want to get rid of some space junk. What do? Well, let's say we throw it outside, and I have my Coke can throwing outside. What happens to that Coke can, depending on which way I threw it, the Coke can will either start orbiting me, or maybe it'll go there and collide with me again sometime in the future. Or of course, it could head back down to Earth, depending on which way I threw it. So if I threw it behind me, it would actually go back down to Earth. That's the correct way to get rid of space junk. Throw it behind you, so it re-enters. Anyway, I thought that I always like that example, so I threw it in there. In any case, right? Let's get back to the question of navigation in space. Let's go say we're going to the moon. Well, the way you navigate in space, the roads in space, are orbits, right? And so those orbits, right, they're given a, actually it's not an orbit, given a position, initial position, right, the set of orbits is going to be constrained. There's a well, actually it wouldn't go like that because it has to have a focus at the Earth. So the best you could do would be like that. Or you could go like that, or you could go like that, right? In any case, you're constrained because your initial position, right, has to lie on that orbit. So you can't just transfer instantaneously between orbits. You have to follow these flights. And so, as we remember, these orbits are dictated by our orbital elements. Right. Now, you can't just change your orbital elements, right? The same way you can't just change your position in space. Because if you remember, we had this whole set of equations going from position and velocity to orbital elements and back and forth. And remember, there's no teleportation in space. You can't change your position, like I can't teleport to ASU. All I can do is hop in my car, add some velocity, and start heading that direction. So the only thing you can actually do in space is change your velocity. Now that does change your orbital elements, and it puts you on a new trajectory, but you don't have complete freedom there. And in fact, if you remember your velocity, there's only 3 components of that, and there are 6 orbital elements. So obviously you're not going to be able to change all 6 of your orbital elements. And which orbital elements you can change and by how much is a very complicated set of equations. And in fact, it's in some sense, it's beyond the scope of this course. We'll consider subproblems of that, certain simpler subproblems, so like the Hohmann transfer and Lambert's problem when we get to lecture 10. But in general, this is a difficult problem, and it's very highly constrained, and it can only actually answer these questions efficiently in very simple circumstances. So that's the background. As I said, right, in this lecture, we're going to be introducing the concept of orbital maneuvers. Specifically in this lecture, we're only going to consider 2D orbital maneuvers, not 3D space in this lecture. So here's our orbit, here's another orbit, maybe there's a transfer orbit. Right. Actually, I should use different colors. Okay. So several possible orbits, right? And how do I get from one orbit to another, right? So as I said, the only thing you can change is your velocity. Can't change position. So I'm here in my orbit at some point in time determined by my true anomaly. Or I can wait and change my true anomaly. That's something that you can change. You can also change time, the time at which you do your orbital maneuver. And you can change velocity, so t and v. And those are the only 2 things we have to work with. Position, velocity at that time and the time itself. So as you can see, right, a much more complicated problem. Or not really, as if you decide to think about it, because, right, when I get in the car is up to me, and how fast in the direction I choose to orient the steering wheel, also up to me. Unlike, however, with my car, in space, the roads are constantly changing with time as you move throughout your orbit. So it would be very confusing if I got in my car at 6 o'clock and the entire road system had changed since I looked up my how to get to work at 5 o'clock. So very complicated. In any case, we'll simplify the system a little bit by only considering coplanar or 2D orbits at this point. When we come to lecture 9, which is the next lecture, we'll consider out-of-plane maneuvers. So that's changing your orbital parameters, 3D orbital parameters, periapse, right ascension of ascending node, and inclination. And then actually in lecture, I believe it's 10, we're going to study Lambert's problem, which is a much more complicated one where we change all of our orbital elements at the same time to find intersecting paths. So this is actually closest to the concept of a GPS, Lambert's problem. I'm pretty sure it's lecture 10, but don't quote me on that. Might be lecture 11. In any case, so I guess we better get started, right? So in this particular lecture, we'll be talking about impulsive orbital maneuvers. So no continuous thrust, right? We assume all of our orbital maneuvers are instantaneous. I'll talk about that a little bit more on the next slide. And of course, we assume changes in delta V due to that. Now, it's not entirely realistic because orbital maneuvers generally take time, so 20 minutes perhaps, or 30 minutes, which is actually substantial if you're close to the Earth, because the period of the orbit when you're close to the Earth is only about 60 minutes, depending, 80 minutes, depending on how high you are. So complicating features, but we're going to ignore them for the most part in this lecture. And then the second part of this lecture, so the first part will introduce these, the steps for for creating a transfer orbit. And then in the second part, we'll consider part B, the simplified case of Hohmann transfers. This is the easiest possible case. And it turns out the most energy efficient for two-burn maneuvers. So just to illustrate, here we have an example problem. Suppose we're in an initial around the Earth circular parking orbit, circular motion, and we want to get to GEO. So this is like perhaps the most prototypical example. So what's our sequence of delta V burns to get us from the parking orbit to our geosynchronous orbit? Let's call it GEO. So specifically, what are our delta V's, and how long is this transfer going to take? So we'll consider both of those questions. Right, so let's consider a simplified case, right? Where we've got a set of current orbital parameters and a set of desired orbital parameters. So let's see, what color shall we associate? So our current ones, with a 0 here, this is where we are, say our parking orbit. And we have a set of desired orbital elements, which is, say, the geosynchronous orbit that we want. Let's just label them for clarity. And these orbits may or may not intersect. In this case, they don't. And we need to find a path to get from the one orbit to the other. So let's think about that problem. We have an initial parking orbit, and we have our orbital elements. We can also consider true anomaly in there, but I deliberately leave that off to some extent because I'm allowing us flexibility in determining when we make the transfer. So we can choose this one as we desire. So we're going to say we can choose this one, and this one is flexible. So these are the constraints on the problem. So as we discussed in previous lectures, those initial orbital elements, of course, give us our position and velocity vectors. So the key constraint here, of course, is the position. The orbital elements that we're given here determine our position vector, initial position vector, with relatively little flexibility. So we're somewhere on this arc. And we can be anywhere on the arc because we allow ourselves flexibility in time. That's okay. So that's a constraint. So what then can we choose? We can choose to change our velocity. So of course, as we learned earlier, these initial orbital elements give us r, but they also give us a velocity. However, we're assuming that we have some thrust in this problem and that we can change our velocity. So the position will be a constraint, but the velocity will be flexible, or we can choose this. If we don't do anything, of course, right, if we just watch, right, we'll continue on this orbit forever, right? There'll be no change, and we'll never get to where we're decided to go. So there's no way we can avoid using delta V to get from one orbit to another. So, except of course if you have like a some kind of skyhook or some energy exchange device here, which maybe you can you can use to give you extra delta V. But let's not consider that. That's in a whole different topic. So let's first talk a little bit about delta V. So we'll talk about delta V in more depth when we talk about rocketry in one lecture. I believe it's lecture 11 or something like that. For more details, see lecture 11. Okay. So again, we assume that these are impulsive orbital maneuvers, so that we have almost an unlimited supply of thrust. So we can make the thrust as large as we can just by building a very big rocket. So our rocket looks like this, right? And here we are right there. So that's basically our assumption. We could prove, but we have a very little amount of fuel in there, right? So we can't burn infinitely hard for a long period of time. So the two components which determine how much delta V we get, of course, are the amount of thrust and the time during which we thrust, and of course, the mass of the rocket itself. Now, in our case, right, we assume that this is infinitely high, this thrust, and hence our delta T is infinitely it goes to zero as we increase our thrust to mass ratio. Right. So in order to I guess, right, find our delta V, right, we just delta V equals F delta T over M, right, just down there, moving the V naught to the other side. Right. Again, we don't consider continuous thrust transfers, although, of course, they're unavoidable because usually you don't have infinite thrust. And they're actually much more energy efficient. You can get much higher specific impulses with continuous low thrust rockets. So this is not ideal, but it's the approximation we're making in this section. Okay. Of course, if you think about it, right, if you actually do a delta V in reality, right, this time is not infinitely short, right, and so you can actually calculate how much position you change, or actually this is position with respect to your initial orbit, right? So how much change in position is associated with this thrust. So of course there is some finite change, and you can just figure it out by integrating position, right? Integrating this once more with respect to time, and then plugging in for the time here, right, into that equation. I think I have the actual explanation on the next slide. Yeah, so you can integrate the acceleration, and you get that the change in position is a function of the delta V that you get, and we can have this plug in the numbers for delta T there, right? And then we get an expression for the actual position that we moved, which notice that that's also a function, the initial velocity comes in there. But again, all of this stuff is being swept under the rug. This is just here for completeness in case you're wondering how much position you're going to be off by. And this can be substantial if you're, say, launching from low Earth orbit where you're moving very fast. in say Kerbal Space Program, you're like it takes quite a while, and so you have to be fairly careful to be constantly changing your thrust vector. But enough about Kerbal Space Program. Right. So let's look at this question here. So we've got here our initial orbit. This is our initial orbit here. And it's deliberately chosen to be a circular orbit so that it doesn't matter where in the orbit we make our thrust. So of course, right, the first constraint on the, so this is a 2D problem, right? So there are actually only two relevant orbital elements, A and E here. So if we look at the constraints on this problem that we've posed here, the first constraint is, of course, that we can't teleport. So our initial, after we make our burn, our position vector will be approximately the same as the position vector after we make our burn. So we can't change our position vector. But we can change our velocity vector. So final velocity does not equal the initial velocity. So if we can change our position vector, but not our velocity vector, what does that get us? How does it change our orbit? Well, let's just think about it. Here we're on our circular orbit. And assume we're going to do our delta V at 0 flight path angle. So let's see which way we're going on our orbit. I think we're going that way. So we have two options, right? We can accelerate, move faster. And what does that do? Well, let's think about it. If we're adding velocity, right, then while we were originally on a circular orbit, once we've added some velocity, right, we're no longer on a circular orbit. And what we've done is move that focus, right? So initially, both the focus and the vacant focus, both foci of the ellipse, were at the center of the Earth. So what we've done in this case is we've added some kinetic energy, which of course means there's a one-to-one relationship, remember, between energy and semi-major axis. So we've increased our semi-major axis. So when we add velocity, that increases semi-major axis. So what that means, of course, is that because this position, right, can't change, this part of the ellipse has to change instead, right? So that's RA, that's RP, and remember RP plus RA equals A to A, right? So because RP can't change, right, what the only thing left that can change is RA. And so when we increase the velocity, we increase kinetic energy, and therefore we increase our semi-major axis and raise our apoapse. Likewise, right, if we burn counter to the velocity vector, right, so we're moving v in that direction, so it's negative delta v, then we're draining kinetic energy from our orbit. Which means we lower the semi-major axis. And therefore, we are going to, well, lower the apoapse, but we were initially in a circular orbit. So actually, what happens is that our initial point becomes the apoapse, and we're actually lowering the periapse. So we lower the periapse. Right. Again, right, this is just a simple illustration of the basic things that happen when you add velocity or subtract velocity from your initial orbit. Right. So let's look at some more generality. So what are all the things, how does velocity influence our orbital elements? Right? So let's look at the equations that we have so far in this class. Right? So all that I've listed here, all sort of the equations that I can think of that are obvious that most directly influence the orbital elements. Right? And so remember, in all of these cases, r is fixed, but we can choose velocity. So if we look at this, right, well, first of all, we're initially in a circular orbit, right? So obviously when we change, we shouldn't focus too much on this equation. This just gets at our initial velocity. So since we can't change, for example, r, right, and we can change v, right, obviously we're not going to be able to maintain a circular orbit if we change velocity. So this equation is not, well, it just tells us that we're going to move out of a circular orbit. The next common one that we run across most often is vis viva, right? And this one's a little bit more useful, right? Because here we've got, remember, this is fixed. And so this sort of indicates that for a fixed r, changing our magnitude of v will directly allow us to determine the semi-major axis. So we can sort of convert back between magnitude of the velocity and semi-major axis directly. And that's sort of what we were discussing on the previous slide, where adding energy to the orbit changes, increases semi-major axis, and negative delta v decreases it. Right? So we can use vis viva, for example, then, to change our semi-major axis. What about eccentricity now? Well, this one's a little bit more complicated, and the relationship is a little bit more complicated. However, if you make certain assumptions, so for example, if you assume that your velocity is occurring at periaps, so you increase your delta v from some circular orbit, for example, then there's a relationship between the velocity at periaps and both a and e, regardless, in this case, of your position vector. So that's something that might be useful. Likewise, there's a closed form solution for apoaps, again, having eliminated the position vector. Now, how did we get from here to here? These are actually new equations for you. All we've done here in this case is we've substituted, in this case we substituted Rp equals a 1 minus e, and in this case we substituted in for there. In this case we substituted Ra equals a 1 plus e. So that's where we got those equations. We just substituted in, did a little simplification, and we got those two equations. Next, here's the equation for escape velocity. I don't know if that helps us too much, right? The position is fixed. It's just telling us how much delta v we need, for example, to escape the orbit entirely. And finally, you may remember from our previous lecture that we had this very complicated formula which gives v as a function of all the orbital elements. So AE, this is a 3D case. Right. So this gives a conversion from a closed form solution for velocity in terms of all these elements. Now this doesn't unfortunately do anything much useful for us unless we know all these orbital elements of our target orbit. In which case we did, we would get velocity. But in terms of inverting these equations, like figuring out what w is as a function of v, much more complicated. So this is hard to use. Although we'll talk a little bit about it, how we can use it in a later slide. Okay. So what are all the things, keeping those equations in mind, that we can do with the delta v maneuver? Right, so here we are, assuming maybe a circular orbit. So first, of course, we talked about it quite a bit. You can raise or lower the periaps. You can add delta v, or you can lower delta v. if you want to lower the periapse. And this one's plus delta V, this one's minus delta V. Right. So that's check, good. Escape, the guy gave an equation for that. We know the velocity we need to escape the orbit entirely. We can change the period, because remember, V determines A, which determines the period, so we can do changes in period. There's a couple here that are related to that last equation on the previous slide. So for example, we can change our inclination, right? Again, this is a 3D maneuver, however, but you can sort of see the relationship between inclination and the required velocity for that inclination. And of course, you can also see the relationship between right ascension and inclination, or right ascension and velocity as well. So if you change your desired inclination, that'll change your required velocity. If you change your your right ascension, that'll change your required velocity. There are limitations to that, strong limitations, however. So for example, you can't change inclination at the highest point in your orbit, right? You can't do it here. And you can't change right ascension at the ascending or descending node. So when you're in the when you're at the equatorial plane, you can't change right ascension. And when you're at the highest point in your orbit, you can't change inclination. It's not obvious how to see that from these equations, but there are other reasons we can argue that. And finally, and perhaps the most important, is you can start a sequence of maneuvers creating a transfer orbit to get you from where you are to your desired destination. Now, this is by far the most common one, right? So the most common case is, right, you're in an orbit, you have a desired orbit, those orbits don't intersect. And even if they did, there are cases where you still like to do a transfer orbit in order to save energy. So in order to get from an orbit, two orbits which don't touch, you've got to start a path. You'd have to take one of those space lanes that we talked about earlier, right? One of those orbital paths to get you from your initial destination, which is your home orbit, to your target destination, which is maybe your work orbit. Or maybe you want to go home, not to work, but home, work. Right. So you've got to choose a path, and you've got to get your velocity onto that transfer orbit. So a couple notes here. I think I mentioned all these already. I will. So inclinations has to best occur to the equatorial plane. Changes in right ascension have to occur above or below the equatorial plane, and all of these out-of-plane maneuvers should be done as far from the planet as possible, for reasons which I'll talk about shortly. Okay. So let's talk about the simplest case. So the simplest case is tangential burns. So this is where there's no change in direction. So the flight path angle occurs at 0. So there's 0 degrees flight path angle. So your velocity simply doesn't change direction, but it does change magnitude. So even if you're, say, here's our planet, and we're going from here to here, for example, we're still assuming even if our velocity vector is not sort of perfect, our initial orbit isn't perfectly circular, that still means we want to burn in the direction of our current velocity vector. So let's say it's that. Then there's good reasons why we do that. The most important is, of course, it is energy conserving. So as we'll argue in lecture 9, if you do a delta V burn not at 0 flight path angle, you sacrifice a lot of energy. And we'll talk about that a little bit more. But so, for example, in space movies, right, you sometimes, right, they're trying to escape the gravity well of a black hole or something. They're always like burning perpendicular to the flight path angle. which is horribly inefficient. It's like a total waste of fuel, essentially. We'll talk about that next slide. But terrible idea. If you're trying to get away from a black hole, don't burn perpendicular to the black hole. Don't burn away from the black hole. Burn perpendicular to the black hole along the 0-degree flight path angle. Okay. So maneuvers typically occurring at apogee and perigee, or periaps or apoaps, depending if you're around Earth or not. And to change, so obviously if you're at periaps, you can raise your apoaps, right? And if you're burning perpendicular to, or opposite your velocity vector, then you lower your, actually, let's see. So here's our initial, we're raising it. Here's our initial, right? We're circularizing our orbit in this case. So we're moving that way. So we're initially on this path, right? And we discard velocity, so we lower our semi-major axis to get us onto our circularized orbit. So in this case, we're probably moving onto a transfer orbit. In this case, we're moving off of a transfer orbit onto a circular orbit, for example. Yeah, we'll adjust that later. So, in many cases, there can be multiple transfer orbits. So if we just go back to my initial question about Siri, how do I get to the moon, right? Siri doesn't know because it's quite complicated getting to the moon. So there's several delta V's, and especially if you want to get back from the moon, right? So let's just analyze those. So for example, we launch, say, from Cape Kennedy, or Cape Canaveral, sorry. Cape Canaveral. That launches us straight up in the air. We eventually turn a little bit. But if that initial delta V doesn't put us on to a parking orbit quite yet. And so if we don't do another delta V, so let's call this our initial delta V, we'll, of course, be on a ballistic trajectory and fall back to the Earth. So that's not a good idea. So we have another delta V here to get us onto this parking orbit. And then we hang out on the parking orbit until the time is just about right. So the moon is, say, in phase. And we use a big delta V here to get us on a path which is not as linear as it looks here. It actually curves like this, but that's okay. And then when we arrive at the moon, right, we want to establish, say, a circular orbit. So this is a delta V plus. This is a delta V plus. Here we want to discard velocity. We're coming in on a very elliptic orbit. And we want to circularize, so we have a negative delta. And then we float around the Earth, maybe drop off a lunar lander. So there's another delta V here. Then we launch, another delta V there. So that's a minus, that's a plus. And then we get onto this circular, back to our parking orbit. We got to have another delta V to reestablish our parking orbit. And then we have another delta V to start heading home. That's a plus one. And then we finally get home, but we're way too elliptical. So we've got to circularize again. So there's another delta V. And finally, we get to where we want to splash down. And we have a final delta V, negative, negative, to re-enter the Earth's atmosphere. So you can think of these things as streets, right? These are several streets, and there are several changes in direction we need to make in order to get from here to the moon and back. Just like there are several turns I have to make to get to ASU campus and back. In this case, there's looks like 10 of them, right? 10 delta V's 10 turns that we have to make to get from where we're going. Now, in this case, of course, there's a lot of flexibility, right, in which path we follow. But the paths themselves are transfer orbits, and those transfer orbits are constrained by initial positions and the position of the target orbit. So each of these paths has constraints, right? Path, 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 another path, another path, right? So there's lots of flexibility in which paths you take, but there's not total flexibility. You have to obey Kepler's laws of elliptic motion. So let's just do a quick example. Say we're in an initial circular orbit and we want to raise periaps. Here we go. Actually, in this case, we're not in an initial circular orbit. We're in an elliptical orbit, and we have initial periaps. This is say when we've arrived at geo. Right. So we had this initial circular orbit. We've done a delta V plus here. We've arrived at geo. But now, if we don't do anything, once we get to this target orbit, to establish ourselves in this target orbit, we have to raise our periaps. So specifically, in this case, our periaps is initially the radius of the parking orbit, and we want it to be the radius of geo. So RP naught, and this is RP desired. Okay. So how do we do this? The calculations are actually relatively easy using those equations we gave on the previous slide. So in particular, we have a initial orbit, right, where we've arrived at apoaps. And we can calculate the velocity of apoaps using those equations, right, that we had before, just by plugging in the formula for apoaps. And so we get a velocity, initial velocity here, which we have on arrival. Now, initially, of course, right, if we don't do anything, then we'll return back to our initial parking orbit, which will just come back like that. So in order to make sure that we are now on a circular orbit, so that we raise our periaps to the circular orbit, to the same as apoaps, we just calculate the difference between our current velocity and the velocity we would need to be on the correct circular orbit at the radius that we are currently at. So if you remember the other formula, one of the other formulas we gave was for velocity of a circular orbit. So now we just plug in the apoaps formula, right? Because we're still at apoaps. We find the velocity we would need to be on a circular orbit at this point. So these are our two formula here. So this is where we are, and this is what we need to be on a circular orbit. And so our delta V is simply calculated as the difference between those two numbers. The difference between the circular orbit, which would be, of course, a larger velocity, and the velocity we're currently at, which is at apoaps here. And so we just take those two numbers and we subtract them off. That's all we do. So let's just think through these steps, right? So in general, we're not going to be able to solve this problem in complete generality at this point. We have to come back to it in lecture 10. But let's just think about it in general. The process is we have an initial orbit we're in for each of these stages, right? From getting each of these legs of the journey, right? We have an initial orbit. Let's color code it something. That's our initial orbit. Here we've got, it's also color coded here. Got an initial orbit. We have a target orbit. That's where we want to be. Let's color code it here. And then we have the transfer orbit, which is how we get from the initial orbit to the target orbit. Right. So three different orbits. Let's see, what color haven't I used? This one. And now in this case, there's multiple possible transfer orbits, but one we've identified in this case is this one right here. Notice that in theory, right, we could actually use the same orbit backwards, but that would be very wasteful, so you would never actually want to do that. Okay. So what are the steps to do to calculating these problems? If you know these three things, then calculating the delta V is relatively easy. Unfortunately, calculating this one is sometimes a little bit challenging. How to get that one. That's actually, in full generality, it's Lambert's problem, and when we come back to it in a few slides, that'll be Hohmann's problem as well. How to design that transfer. Oh, sorry, it's not. I have target orbit. This one. My bad. Yeah. So let's consider the problem, right? Suppose we have all these three things. So we've got our orbital elements for our transfer orbit, and here I've included time, although again you have some flexibility on time, so we can choose this one. So the steps are then to choose a true anomaly at time and calculate the velocity, right, of your transfer orbit at that point. So that's VTR1. And then we calculate our velocity before before the burn, which is V1 minus here. It's on the slide. And so to get from our initial orbit onto that transfer orbit, we got to do a delta V maneuver, which is this one right here, delta V. So in that delta V maneuver in 2 dimensions or 3 dimensions, this is 2 dimensions, is just the difference between that transfer orbit velocity we got in the initial one. Again, right, we use that solution we got in the previous slide, lecture 7, right, where we used our orbital elements to calculate R and V. Right? So we've done that twice here. We've done it to calculate this number, and we've done it to calculate this number. Right? So that puts us onto our transfer orbit. Notice that calculating the transfer itself can be very hard because, of course, you may not know what the times will be on your transfer orbit. It's a very, very, very difficult problem, actually, in general. Again, we'll consider the special case of the Hohmann's, where it's much easier. But generally speaking, step 1 is the hardest. Okay. So now you're on your transfer orbit. Let's see, what was I color coding that? I don't know, maybe yellow. And I'm pretty sure this was my desired orbit. Here, I'll just continue. Oh, no, not that one. Continue that transfer orbit up there. And so now you get to the point where these two orbits intersect. And presumably you design your transfer orbit so they do intersect. And you calculate the time at which you intersect there, FTR2. And you use that to get your velocity at that time, right? Because you have all the other orbital elements of your transfer orbit. So you get the velocity at time 2. Now that's this vector here going that way. Now you calculate the same velocity vector for your desired orbit at that same point, right? And again, right, it's relatively, both of these steps are relatively easy to do because you can solve the polar equation. So remember R, you know the radius, if you know this position vector, you can use that R to get you both FRT at 2 and F on your desired orbit. Right, so you can get both of those numbers. So then, armed with those true anomalies, you can get the velocity vector of on your desired orbit, your final orbit. And then, of course, you need to be at that desired velocity. And so the delta V maneuver 2, right, is just the difference in those two velocity vectors. So your second delta V burn moves you from that transfer orbit at the second point of time to the desired orbit at that same position in the orbit. So that's that's the sequence of steps we take to solve this problem. Again, right? Generally speaking, if you have that intersection point, it's relatively easy to calculate these true anomalies. If you don't, however, it's a little bit more complicated. Now, of course, that doesn't say anything about how we design this transfer orbit, and that, again, is what I was talking about. That's the most challenging problem. And we'll consider a couple of different ways of doing this. So first we'll consider Hohmann transfers. Then we'll consider so elliptic homotransfers, then we'll consider bielliptics, and finally we'll come back to Lambert's problem. So in lectures 8, 9, and 10, oh, and also don't forget plane changes as well. So in lectures 8, 9, and 10, we're going to consider several different ways of designing those transfer orbits and go through them all very carefully. Because that's the path planning problem. That's your GPS in space, those transfer orbits. Okay. So constraints, of course, your transfer orbit has to intersect both orbits. So say this is your desired, this is your initial, and here I've drawn a transfer orbit, or someone else has drawn it actually. Let's see, be consistent in our color coding. Transfer orbit. It gets us from orbit A to orbit B. Now you may think, right, why did I even need a transfer orbit? And that's why I draw. This is a very nice picture. Because actually these two, the initial and desired orbits, actually intersect, right? So you could just do a massive delta V burn to move from this orbit to this one. However, that conflicts with the second set of advice I gave you earlier, which is that always do your delta V burn along the flight path angle. 0 degrees flight path angle. So, in fact, there's a conjecture. There's a conjecture. It has not been proven. This is an open problem. I believe it's still an open problem in orbital mechanics that the energy optimal two-burn maneuver between any two orbits is always a 0 flight path angle burn. So yet to be proven, but I believe, as I recall, but it's certainly numerically we found it to be the case. Right. So actually, this big transfer orbit over here, right? Even though this is a negative delta V burn here, this is positive delta V burn, is more efficient than just doing a instantaneous burn at the intersection of those two orbits. Of course, right, it's also very much less efficient, right, because it takes significant delta T to get from while you're on that transfer orbit to get from here to here. Whereas if you just did a big delta V burn there, you'd instantly, actually, I should actually be going that way, so that would be less efficient. But anyway, so obviously I could do this instantaneously if I just did it here, but it's not energy optimal. And this is a constant trade-off between time it takes to do these maneuvers and the energy it takes to do these maneuvers. So generally speaking, the more time you have, the more efficient you can do your burn. And this is when we see the bielliptics taken to an extreme case in that case. So if you're feeling punchy, you can always try and do that proof. So let's consider this problem, setting ourselves up for the Hohmann transfer, where we've got sort of a very special case, but not too special, where we're trying to move between two circular orbits. And this is not uncommon, right? And again, one of the most common ones is the geosynchronous orbital configuration. So we've got an initial circular orbit, and we've got a final circular orbit. And what is the sequence of maneuvers that we can make to get between those two orbits? Well, obviously, there's all sorts of paths that we can take, right? We can take this one, or we can take this one, or we can take this one, or we can take this one. Hey, we could even like reverse our velocities and go like that, which would be very inefficient. I don't recommend it. All right, so there's all sorts of choices for this transfer, right? So let's see if we can parameterize all the possible transfer orbits. How many degrees of freedom do we really have in space? We don't have unlimited, right? There's only actually 2 degrees of freedom that we have. So let's consider the constraints. So obviously, for our transfer orbit, several transfers. So obviously, the initial circular orbit, right? the initial point on our orbit has to be r1, and the final orbit has to be r2, right? So when we get there, we have to be at r2, and when we leave, we have to be at r1. So what does this constrain? So if we look at this, it means that on our transfer orbit, assuming that r2 is greater than r1, that our periapse has to be greater or less than our initial orbit. Right? So the periapse of our transfer orbit has to be less than our initial orbit. Otherwise, these don't coincide, right? So it can be less than, but if it's greater than, right, you'll miss your initial orbit. So you can't have that. Finally, our apoapse has to be greater than our target orbit. So we require apoapse to be greater than r2. Otherwise, we'll never get there, right? We'll just return back to the Earth, right? So this, remember, apoapse, farthest point in the orbit, and this is the closest point in the orbit to the Earth. So obviously, these are two constraints that we have. And so given those two constraints, we can define two inequalities. So if we just use our formula for periapse, right? That's our formula for periapse, and there's our formula for apoapse. That gives us two constraints on the orbital elements. Here we've defined the orbital elements in terms of P and E because it's a little bit easier to visualize. So if we put that as a set of constraints, since R1 and R2 are known, we can rewrite those constraints as in this form here. So if we just solve then for E, for example, as a function of P, we can plot the constraints we have on the parameters of our transfer orbit. So this is P, right? And the vertical axis is E. Horizontal and vertical axis. And so we can see that, right, the first constraint on periapse, right, on apoapse, requires our E to be greater than 1 minus the semilattice rectum. So that gives us this constraint right here. So this is R2, right? And then, this is R2. And then the other constraint is that E, so this is E, right? So E has to be greater than, we have a slope here, 1 over R1, minus 1. So our intercept is down here at minus 1, and here our intercept is at 1. So constraints on eccentricity, right? So in this case, eccentricity, if we're looking at it here, we got another line, minus 1 intercept, slope of 1 over R1. And the intersection here, of course, at E equals 0 is just R1, P equals R1. And so we have to be above this line, and we have to be above this line. So they intersect here at some case of minimum eccentricity, right? Minimum eccentricity orbit. And that, of course, actually gives you what we'll talk about next, which is the Hohmann transfer. Right. So all of these orbits down here, right? All of these transfer orbits here are ellipses because the eccentricity is less than 1. Right? At some point, right, we can get parabolic transfers, right? These are probably like that, parabolic. And then at some point we'll get elliptic or hyperbolic transfers when we increase our eccentricity beyond the threshold of 1. So that's up here. So maybe that's that one. That's the parabolic. And then the ellipses, get rid of that and make it a different color. These are the ellipses. So again, lots of choices of our transfer orbit. However, right, given a choice of E, given a choice of E, if we specify our E, for example, E desired, then we have our P must lie somewhere in that region. As we decrease E, we get to some critical E of the Hohmann transfer, and then there's only one P that determines our orbit. So this gives you some idea of the flexibility that we have in choosing our orbital elements. They have to be constrained to lie in there, in that region. Likewise, of course, if you chose a P, you can look at your possible values of E for that transfer orbit. So finally, I'll just give a brief shout out to lecture, I believe it's 10. In the general case, right, we're looking for the general way of transferring between point 1 and point 2. So say this is our initial orbit and that's our target orbit. That is Lambert's problem. So Lambert's problem is we have a initial position, we have a final position, and we have a delta t. And those three items almost sort of uniquely define, I say sort of because there's actually two or three options in the general case, but more or less uniquely define the transfer orbit. I say unique because actually you can go backwards on the orbit as well, and so there's some flexibility. We'll get back to it when we talk about Lambert's problem. So that's how you would solve the more general case, to design, again, these transfer orbits. Right. So as I said, right, earlier on, the whole kit and caboodle, so to speak, is picking that transfer orbit, finding that path from point A to point B. And in the most general case, where you have a time constraint, it's Lambert's problem. Find me the fastest path from A to B. If you have energy constraints, however, it's Hohmann, and we'll come back to that very shortly when we consider Hohmann's problem. So at this point, I'm just going to take a quick rest and come back when we talk about Hohmann transfers and energy optimal transfer orbits.